Welcome everybody. Peace and love. Hope you're well. This week we're going to be talking about units 29, and in this particular whiteboard session, that's what we're going to talk about: the interior of the planet. What's down there? What's down there? What's on the inside of the Earth itself, beyond the rocks that make up the crust? That's what unit number 29 is all about. We've moved past the atmosphere and the weather, things that we're very focused on for the kind of the middle part of the course, and now we're focusing on the lithosphere. So I've got a lot going on here, and I'll start and begin by explaining, really this is the Earth's interior that I've drawn out for you here, and in the slides that I provided to you guys, there are other illustrations as well. So I'm going to try to knock all of these out all at once, okay? Essentially what we've got going on, if we look at this as a whole, what I've got are four different layers, four different major layers of the Earth, okay? And those four layers are like color coordinated as I have illustrated on this board. So the red is our crust, okay, our crust. The crust's material is a very hard, thick, I shouldn't say thick actually compared to what the rest of it looks like relatively speaking, but hard rocks, mud, clay, that kind of stuff, okay? That's the crust of the Earth. And it's also very rigid. Meaning that it can break very easily. If there's pressure applied, it can actually break and split apart. Okay, it can actually break and split apart. Crust, yeah, that's on the outside layer. That's the surface of the Earth. That's what we all stand on, work on, drive on, dig through as human beings. Yeah, the crust. Next, in the blue here, okay, we have something known as the mantle. Okay, mantle. And mantle can be split up into two different kind of sub-layers. Technically speaking, we consider both of those as one, the mantle. But it is important to know the differences because they do vary between what's known as the upper and the lower mantle. Upper here and lower mantle. So I did a kind of a dotted line to designate the difference between the two. Okay. I don't know if you guys can make out this number, but the distance between where the surface of the Earth is and the upper mantle, that's about, actually the surface, that would be between where the surface is and then right where the upper mantle is. Not very much. It's only a few hundred miles in some cases, even less than that in other places, okay? This thickness here. Now, between the crust and the lower mantle, where the dotted line is, if this is considered our lower mantle here, okay, lower mantle here, then we've got a distance of 1,385 miles, okay, 1,385 miles. Yeah, difference between upper and lower and why they matter. So the upper is considered less dense, okay, so it's less dense. It's still, well, let's put it this way. The upper is where the lava is. And so when this crust breaks, the lava from the upper mantle is forced up through that in many cases, as we'll discuss more and more. But what ends up happening is that lava, which is much less dense and much more flexible, the author refers to this as kind of like plasticky material, which is an odd way of thinking about it, but if you think about plastic, if it gets heated up, it's flexible, it's kind of gooey, right? So it's not exactly liquid, but it's not exactly solid. For all intents and purposes, that's what's in the upper mantle, okay? Now, below this 1385, and then we go to 1,800 miles, so in this space in between, that's the lower mantle. And the lower mantle is solid. That's going to be solid rocks. Okay, that's going to be kind of a solid rock. So that's why there's a difference between the two things. Even though they're technically considered the same layer, the mantles, they are different from one another. It's almost like the solid rock kind of gets heated up into the point where it's this kind of flexible, quote-unquote plastic state, right? Like I said, if plastic gets heated up, it becomes flexible. That's what the upper mantle is all about. Beyond that, so we go from hard, kind of in between, hard, and then we have something called the outer core, which is 100% a liquid kind of material, okay? 100% a liquid type of liquid metal kind of material, okay? Much more liquidy than the upper mantle itself. That's the outer core, and that would be, outer core starts from 1800 and it actually ends at 3200, okay, miles within. So this green here, outer core. When we get to the very, very bottom, right down, if we dug as far as possible, we would get to this thing here called the inner core. And that is completely solid inner core. We know that because there's much higher pressure there. But yeah, basically what we're talking about is solid iron, nickel, rocks, etc. Right? Some of the hardest stuff you could think of possible. That's what's going to be in the inner core. All right. So we have solid, liquid, solid, liquid, kind of in between. But again, the mantle is all considered the same thing. And then once we get to the crust, we have another solid that is very breakable. Okay, very breakable. How do we know this? Okay, so it's important to know how this is even possible, how seismologists and geologists came up with these theories, right? It's not exactly something that we could send a ship down the middle of the Earth and figure this stuff out. So this was figured out through seismology, which is measuring earthquakes, which is known as seismology. Okay, and so seismographs, and the author has a better illustration of this in the slide deck. But seismographs are little instruments that are used for measuring how intense an earthquake actually is, how intense the shaking is. And so those are all over the world. And when an earthquake occurs, in any place, okay, hypothetically speaking, in any place, the intensity of that earthquake is going to be recorded by multiple seismographs throughout the entire Earth. So if we have an earthquake here on this portion of the Earth, and again, this is just hypothetical, if this is an earthquake, what's going to happen is there's going to be waves that are going to be emitted from that earthquake, okay, waves into the interior of the Earth itself, waves. And so these, shaking, and these shaking waves, they come in two different forms, P waves or S waves. P waves, and both of these different waves, by the way, are recorded by these various seismographs that I've illustrated. And there's much more than 4. There's thousands and thousands, but I'm just doing this for illustration purpose. Anyways, the P waves, so the two different types of waves let off. The P waves, if I have in black here, your P waves, we know that they travel through solid and liquid. Okay, solid and liquid. P waves travel through solid and liquid. And so if an earthquake happens in, let's just say, the north part of this illustration, it can travel through all of the solid material and the liquid material in the outer core, then again through the solid, and kind of all the way down to the very bottom of, the opposite side of the Earth, into these seismographs here. So on the other side of the Earth, the seismographs can record, because of P waves, what happened on this earthquake up there, all right? And S waves, however, okay, S waves in red, do not travel through solid liquids. So they only travel through solids. S waves only travel through solids, not liquids. Therefore, again, an S wave would come through, and if it was an S wave like this, it would travel through the solid, even the mantle, it would travel through the solid, but it would be stopped by the outer core, which is completely liquid. Not to say that no S waves are recorded, because there are seismographs in other parts closer to where the epicenter of the earthquake happened. So maybe the S wave made it through the solid here, but it didn't even manage to reach all the way down to the S wave in that direction. Or it wasn't directed in this way, to this seismograph, right? But if they were directed kind of straight through, they would be stopped by this liquid outer core. And so those are the things, the two different types of waves, and what we know about the waves. That information allows the scientists to understand exactly what the type of material is inside the Earth, okay? And then, for that matter, where do these layers begin and end? Where do they begin and end? Last point I'll make, the Earth itself, from the crust to the very center of the inner core, so the radius of the Earth itself, 3,959 miles. For all intents and purposes, 4,000 miles deep. That's how deep the Earth is. Thank you. Well, let's go ahead and talk now. We'll look at the key points and kind of finish up with 29, and then we'll just move right into 30, as they're closely related to one another. There is a separate quiz for 30. Just be on that if I have posted that to you guys on Canvas. Anyways, it's good to know both these things. We can knock them both out at one time here in our lecture. We saw on the board the different layers, and I did want to mention just a couple other things about the crust itself. The crust, the very thin layer, okay, very thin layer relative to the other layers. Very thin. The other layers are hundreds of miles deep, whereas the crust itself would be a very, very thin. I mentioned a few hundred miles, but it's not even nearly that. So don't take what I said in the video to be true, because now that I'm looking at the notes, it's nowhere near that deep. The fact of the matter is the crust is only about 25 miles thick under the most, the thickest land masses, the continents themselves. And then under the ocean, it's even thinner. So under the ocean, it's only about 5 miles thick. And this is completely variable throughout the Earth. There's what's known as undulations, where the crust is kind of doing this, right? Because there's topography on the Earth itself too. Not just above the surface where we have mountains and valleys, etc., but underneath the Earth itself. Underneath the oceans, there are undulations as well. So the thickness, when we talk about how thick this is relative to the other layers, it's like an example of an egg, the shell of an egg, right? The shell of an egg. If you hard boil an egg, and then you peel that shell off, and it's like, paper thin. Imagine that is the crust, and everything else is the rest of the Earth, what's down there. In fact, it's even thinner than that, to be totally frank. But to give you the best example I can think of, it's that thin of a layer compared to the others. Let's see. So the zone between the crust and the mantle is called the moho. That's important to know. MOHO. And the lithosphere, so the crust, it is not. I mentioned this before. It's rigid, meaning that it can break easily compared to that kind of liquid type of plastic state. That's not quite a liquid, not quite a solid. That's in the upper mantle. That stuff is flexible, right? That lava is flexible, whereas the crust is not. And so when the crust breaks, when the lithosphere breaks, okay, when it breaks, the less dense layer of molten lava, okay, in many cases it will rise up through the crust, and that's what we have with volcano eruptions. That's where lava comes from the upper mantle, okay? And it's the fact that the crust itself can break very easily if under pressure, okay? Break very easily. Now the next topics start to shift into chapter unit 30, okay? So unit 30 now. And the next thing to mention here is that the lithosphere, when I say lithosphere, I'm talking about the crust, okay? So the lithosphere, it's discontinuous, and that means that it's not all kind of connected to one another, for all intents and technical purposes. So what we're saying is that it's fragmented, and it's fragmented into a number of different segments. And these fragmented segments, they're called tectonic plates. So it's not continuous, tectonic plates. And we know that everything below it is this kind of, lava molten plasticky state, and and it's less dense. And so that stuff that is flexible, it makes those plates actually kind of float around and move around. It makes them shift around and move. So they don't always stay in the exact same place all the time, every day. They actually move frequently, a lot. Those plates are constantly moving. Something known as orogenic belts. Those are a series of linear mountain chains with high relief, and they form where plates crash into each other. Okay, and then the rocks get uplifted like this, kind of like a giant accordion, like this. Orogenic belts, linear mountain chains. And you see kind of mountains on the earth, kind of doing this pattern, all in the same, kind of like a straight line. And that's because plates crashed into each other and kind of did this kind of pattern. Okay. Here's 35. Just to give you an example of some of the orogenic belts that are on the Earth, some of the big ones. I mean, there's a lot more than this, but these are some of the big ones when it comes to identifying those linear types of mountain ranges. There's a lot of volcanic activity here, in many of these examples. Not all, but many of these examples. And there's also a lot of mountain ranges. I mean, that's basically a correlation between these orogenic belts and big, tall mountain ranges that you're going to find. Okay. Here's the Himalayas, and look how thick this little belt is, right? And these are the tallest mountains in the world. Here's the Rocky Mountains, and they kind of go through this pattern here, this linear pattern. Sierra Nevada, same thing, okay? Andes Mountains on South America, same thing, okay? Now, there's a guy that's very important named Alfred Wegener, and this is in 1915. And so really, when you think about this, it's not that long ago, only about 100 years ago that the scientists kind of figured this stuff out. But Wegener's hypothesis is that the Earth's land masses at a point in time, okay, they were all connected to one another. When I say connected, again, remember there are plates, so they were constantly shifting below the surface of the Earth, but where the land masses were, they were connected, okay, to one another. And that made up one large supercontinent, and that so basically all the land in one place, and all of those, that one supercontinent was known as Pangaea. Okay, this was during the Paleozoic, Mesozoic eras, when dinosaurs were roaming around, basically, is what we're talking about. Hundreds of millions of years ago is when this Pangaea existed. Now, Wegener hypothesized that there was a notion that the continents, like we just said, they float around. And so the analogy that he uses, that they were mobile, almost like they were like giant rafts, because below is this flexible kind of material, not quite liquid, but not quite solid, kind of flexible material. And so then the plates themselves would kind of shift and move around, almost like they were giant rafts floating in the ocean, something like that, right? And this whole notion that he's talking about is known as continental drift. Drift would be that they are slowly moving away from each other, into each other, side by side, whatever the case may be. The direction doesn't matter. We'll get into that in a minute here. And so this continental drift led to the breakup of Pangaea, okay, and it became a slow movement to where the continents ended up in their position of where they are today, okay? Now, that's not to say where they are in 2020 is going to be their permanent position forever of all time. No, if we look at this 100 million years from now, they could be in totally different parts of the Earth, right? Because of continental drift and Wegener's notion. Check out YouTube. Let's do that now, and we'll come back and talk about the rest of tectonic plates, boundaries, etc., like that.
Talk about the ultimate breakup. Europe and Africa have been splitting apart from the American continents for millions of years. At a rate of approximately 2.5 centimeters per year, the continents are moving about as fast as our fingernails grow. And as they continue to split, the rift between them, otherwise known as the Atlantic Ocean, will get even wider. And all this drama is leaving behind a major scar, an underwater valley called the Mid-Atlantic Ridge, which tears more and more as the continents slowly move apart. Looking back on the continental relationship puts us a mere 300 million years ago, when Africa, Europe, the Americas, and all the other continents were one big landmass, the famed supercontinent, Pangaea. Due to the constant churning of magma underneath the Earth's crust, they all split up and moved to their modern-day positions. But if destiny in the form of magma and tectonic plates has anything to say about it, the continents might have a chance of getting back together. But how will these stubborn continents kiss and make up? Scientists believe the plates will shift, causing the continents to rearrange and get back together. But in true tectonic plate style, it'll take about 250 million years. Our planet has a violent soul. Majestic and often destructive, volcanic explosions rattle our collective imagination.
Okay, a shorty but a goodie there. Yeah, and let's discuss more now. This is really chapter 30, getting into understanding the rocks on the Earth and getting into some real deep kind of geological discussions now. So it was in the 1960s, okay, 1960s, and there was this thing called sonar technology. You know, sonar, a beam is sent out from a sensor, goes out and contacts something and then comes back. And so the distance between the time it takes for that kind of relay to happen would be the distance of something. And so sonar technology would be mounted to ships and you know, the bottom of a ship. And so these beams would be sent out from the bottom of the ships towards the bottom of the ocean and the surface underneath the ocean. And so sonar technology enabled ocean floors to be mapped and to be understood in much greater detail. You know, again, before this, people really didn't know, scientists really didn't know how deep this kind of stuff was. And there still are some areas that are like that, but most of the ocean floors at this point in time have been completely mapped to a pretty great detail because of this type of sonar technology. And the technology itself has gotten much better over time to make these maps more accurate and more precise. So what the scientists noticed, a couple things, and that was that the rocks beneath the very deep ocean floor, those rocks, you know, they would go down and take samples of those rocks, and those rocks were found to be much younger in age compared to the rocks found on continents, okay? Much younger in age compared to rocks on continents. And so let's pull up next PowerPoint. Let me there. Okay. And we're looking for number 9. Get rid of this one now. Okay, so here's what we're looking at, the age of the lithosphere, the ocean in particular. And the redder, the more red the illustration is, the younger the rocks are compared to the green to the purple, right? And so yeah, that's saying under the ocean in many parts that the rocks, you know, they're not as old. And why? What's going on with that? And so the explanation is that there are there's ridges underneath. So along with understanding that they're younger, having an understanding of the topography that's down there, right? That's down under the ocean. Ridges, so not just that the ocean kept getting deeper and deeper and deeper and deeper. There are parts where
from the surface where the water is, kind of can go down, 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 and then actually parts can go up, up, up. So there's like underwater mountain ranges. That's what this sonar technology revealed in one aspect. And then it also uncovered this younger rock thing, which is because the discovery is that the younger rocks come from um, hot rocks, hot lava, okay, hot lava from tectonic plate movement underneath the ocean, hot rocks from the mantle rising and then spreading the seafloor apart, okay? This is known as seafloor spreading. And so then you have essentially brand new rocks that are formed because when that very hot molten lava hits the water, well, then it automatically cools and becomes new rocks. And so that's how the scientists were able to come up with these type of conclusions in the age of the rocks. Okay, and again, we're talking millions of years apart from one another, but still, it's pretty significant discovery. So here's the example of the seafloor spreading. Okay, where you've got plate movement moving away from each other and molten lava kind of pushing upwards and forming this new, let's call it a new seafloor, okay, new rocks to take up the place where the other ones were pushed apart from one another, okay? That's what seafloor spreading is, which has happened in many, many places on the earth under the ocean. Many of the oceans themselves have this type of phenomenon. Yeah, so we mentioned this already. The lithosphere is broken up into tectonic plates. And this whole theory now, as it's recognized, you know, very much so by modern day scientists, we call this plate tectonics. So plate tectonics is kind of not just the movement of the plates, but also formation of new rocks, destruction of old rocks, um, and continental drift, earthquakes, volcanoes, mountains, really all of the above is the study of plate tectonics. Okay, so plate tectonics. It's part of geology, geology with an L, geology, not geography. I mean, this is physical geography, obviously, which is a more broader explanation. But for somebody that really wanted to study plate tectonics, they would get into geology. Okay. Okay, so the plates on the Earth. Well, there are 9 really large plates, and then there are several other much smaller plates found on the Earth. So 9 very, very large plates, like continent size, and then there's hundreds of other much smaller plates as well. So looking at examples of the different plate boundaries, and then also where um, uh, active volcanoes are and active earthquakes. So we can map out the plate boundaries based on where earthquakes have occurred and where volcanoes appear, right? And that kind of thing. Because earthquakes are, we'll see here in a moment, earthquakes are a result of plate tectonics, plate movement and continental drift, in particular plate movements as we'll get into very shortly here, crush into each other, move apart from each other, or drift side by side, okay? Here's the big plates, okay, that we know, the world tectonic plates. So here we have the land masses in gray, and then everything else is colorized by some type of unique plate. The largest one would be the Pacific plate here, the Pacific plate, which takes up, if this is North America and this is Asia, takes up a big, big, big portion of the Pacific Ocean itself. Yeah, the Pacific Ocean itself. So when the Pacific plate, for example, crashes into the Australian plate, as we see the arrows, one going this way, one going this way, that's going to create earthquakes along this line here, and what's known as a plate boundary. So plate boundaries are suspect to major earthquake type of activities. For those of us that live in California, look at what we have, okay? the edge of the Pacific Plate and the North American Plate, okay, the North American Plate itself. And they are, in many instances, crushing into each other, okay? Hence, why do we have earthquakes so much so in California? Also big mountain ranges too, okay? Also big mountain ranges too. Let's see. So the plate tectonics, the movement itself, it's not all the same everywhere. And in other words, how much plates, shift and move and drift from different in different directions. Not all the same. So, like for example, the North American plate doesn't always move exactly the same amount as the Pacific plate or the Eurasia plate or something like that. There's a range. Okay, so there's a range. So geologists and land surveyors can measure this, and they do so, for practice. Tectonic plate movements ranging from anywhere from, let's just call it half an inch to almost 5 inches per year. So that means somewhere that you find on the surface of the Earth technically could have moved 5 inches from one year to the other. Okay. Now that's, again, we're talking the extreme ends of the spectrum there. And like I said, different parts of the world shift differently, right? Different plates have different velocity than others. Let's talk about the different plate boundaries when these plates crash into each other, okay, causing earthquake activity. There are three major boundaries I want you to know. Remember this, 3 major boundaries, okay? So if I ask you about specific earthquake or plate tectonic plate boundaries, I want you to understand these 3 type of boundaries, okay? The first one is known as a divergent plate boundary with a D, divergent plate boundary. And that's when the crust, it drops between faults and it forms this rift valley along what's known as the divergent plate boundary. So in other words, the plates move apart from each other. They move away from each other, okay? They move away from each other. They diverge from each other, which is what we've seen in those examples like with the map and the young rocks. The young rocks are a result of the plates moving away from each other because of divergent plate boundary activity, okay? Rift, like they're moved apart from each other, and then what are you going to end up with? A valley, right? So the Atlantic Ocean is just in itself, right? The Atlantic Ocean in itself, the ocean being there and continuing to be there, is a result of 2 divergent plate boundaries that moved away from each other. And I shouldn't put that in a past tense. They are continuing to move away from each other, okay? So the Atlantic Ocean is continuing to get wider and wider every single year because of divergent plate boundaries, okay? So the Rift Valley underneath the Atlantic Ocean is getting larger and larger and larger, okay? 1920. Okay, here's divergent boundaries. Yeah, we saw a little bit of an example of this already. So imagine we have solid lithosphere here, and then we've got molten lava, of course, in the upper mantle. And that stuff is creating pressure on the crust. That's the other thing, right? And so in a weak spot, we've got this, especially when the plates are moving apart from one another. They're pushed also apart from one another because of the molten lava from the upper mantle. And so that ends up creating this rift here. And so what do you get if there is no more land? Well, eventually you're going to have some kind of water, right? Some kind of water. So deposits from the dense rock and mantle create low-lying relief. Low-lying relief, you end up, rain events and other type of drainage, then there's going to be water there eventually. And then it's going to be permanent water because it's not going to move, right? Because there's nowhere for it to go. Then the deposits from the molten lava basically create the lower surface underneath that where that water exists. And this is an explanation of, like I said, the Atlantic Ocean, okay? There are other places on the Earth where we have these rift valleys. It's not just oceans. Some of them are technically on land. Africa has some very large rift valleys. So yeah, here's some examples. And like I said, it's not always the large plates. Sometimes it's the smaller plates themselves that don't that we didn't see on the map earlier. These smaller plates, same type of plate activity. In this case, divergent plate activity that is causing these type of scars and permanent type of residual effects on in this case, on the landmasses themselves, creating very, very large valleys in Africa. The next boundary I want you guys to know is something called the convergent plate boundary. So if divergent means moving away, convergent means coming together, okay? Coming together. Two plates come together, okay? Two plates come together. There are a couple different things to consider here. If you have an ocean plate and a continental plate, the one that's less dense, which is the continental one in most cases, it's going to override the denser ocean plate, and it's going to cause it to sink downwards in a process known as subduction. Okay, so the ocean plate actually sinking below the continent plate. That's known as subduction. Okay, and what we see in the west coast of California, Oregon, Washington, okay, those are examples of ocean and continental convergence plate boundaries. Okay, because of it's known as it's called what's known as a subduction zone. A subduction zone. Here we go. This is the example I'm talking about. And so you do end up, because you have one plate going under another. In many examples, we have this kind of very tall mountain ranges right up against cliffs and other things like this, right up against where the ocean itself is. Okay, because of this continental versus ocean plate convergence coming together. Ocean plate goes down. Well, the continental plate has nowhere to go, but in many cases up, creating these ranges of mountains and cliffs. Okay? Here's an example where the molten lava from the upper mantle is kind of wedged in between, and look at that, actually ends up creating a volcano. Not every single case is going to create a volcano, but some cases they are in the convergent boundaries. Okay. So yeah, we talked about this. Subduction zone is intense tectonic and volcanic activity. And then the other thing known as a volcanic island arc. That's when two ocean plates converge with one another, okay, and they crash into each other. And that's going to create volcanoes in the middle of the ocean. And then those volcanoes are going to be spewing out lava, and eventually those lavas are going to turn into rocks. Well, what ends up happening is that rock has to harden, or that lava has to harden into rocks, and then that rock becomes an island, right? It becomes an island. That's what Hawaii is. It's just a collection of volcanoes. Because of convergent plate boundaries, two ocean plates converging together, okay, basically creating volcanic activity, and molten lava underneath, pushing outwards, spewing out the top, because we know now the lithosphere is very brittle and can break. Okay, when the lithosphere and the crust breaks, that's when you have volcanic activity. And volcanic island arc is really a telltale sign of this types of plate boundaries and plate activity. Okay, take a look at 28 through 30. Okay, so here's the example of, we already looked at something like this, but here's ocean to ocean, okay, subduction, and creating this kind of island of, again, because the plates, they're going to be close to each other and kind of linearly. And so very often you see the islands kind of in these straight lines, okay? The other thing that I wanted to mention, before we look at this very last one here, well, how about this? Okay, we're still on the topic of convergence, so I'll just keep it on the screen. Convergence, like we said, it's when plates come together, when they meet each other and they crash into each other. If there's a continent and continent, two different continent plates crashing into a convergent plate boundary, you're going to end up with the plates really with nowhere else to go, and they thicken and then they go upwards. Like we said, like an accordion. So they will create these, very vast mountain ranges, but really little to no volcanic activity. So like the Rocky Mountains, for example, right in the middle of the country, and no ocean plate nearby. And so not really much volcanic activity in those examples, but we do have very, very, tall, extreme terrain in those mountain ranges. Those would be continental and continental plates, convergent boundaries coming together. Okay. Now the last one I want you guys to know is called the transform plate boundary. Transform, and that's when two plates they slide into each other. Let's see if I can do this with my hands. They slide into each other kind of horizontally. Okay. They slide past one another. So they don't crash and they don't come apart. They just kind of slide side by side. Okay. So it's almost like they're grinding into each other. Okay. They grind into each other side by side. Okay. Um, in California, the large fault called the San Andreas Fault, that's from a transform plate boundary. Okay. That's from a transform plate boundary. And there's earthquake activity in transform plate boundaries, but there's really no volcanic activity. Okay. Hence the reason we don't really have active volcanoes in California when we have earthquakes on the West Coast, because of this transform plate boundary stuff, right? And let's see. So this sliding between each other is fairly quickly, and so that's about a 2 inches per year um, 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 grind between one another. So, like I said, there could be places in California where you look at one day, and then 2 years later, and then a year later, it's 2 inches apart from where you measured it the first time. And that might not sound like a big deal, but let's multiply that over thousands and hundreds of thousands and millions of years, and you can see how plate tectonics we end up with the land masses and the oceans, etc. Really, the constructs of the lithosphere in the locations and the places that they are, which is the focus of why physical geography in the first place. Looking at 32, just to wrap this up. Here's an example of transform plate boundary. Okay, like I said, sliding apart from one another, and things that used to be maybe continuous next to each other, now there's a shift where they're not so much so the case. Okay. All right, that's going to do it for both 29 and 30. Hope you enjoy. Unless otherwise stated, there are 2 separate quizzes on this. So you might need to go back and watch it in 2 different phases, whatever is up to you. For 29, we talked about the interior of the Earth, the different waves that make up the Earth, or the different waves that make up or result of earthquakes, and then how we come to those different conclusions. Okay. We discussed the crust and the lithosphere in pretty good detail, and broke it down into tectonic plates, and understanding that these tectonic plates move like rafts. Okay, and so at one point in time there was a place called Pangea where all the continents were completely together all at once. They have moved apart considerably since then, and sonar technology has really helped scientists understand what's going on with the geology and the terrain below the surface of the Earth, or I'm sorry, below the ocean. Okay, below the ocean itself. And we learned that because of these different, in particular, divergent plate boundaries, the rocks on the many parts of the ocean itself, where rift valleys exist, the rocks are very, much younger. And so they kind of correlate with one another. One explains the other, kind of both back and forth. Other plate boundaries that are important to know are convergent plate boundaries and transform plate boundaries. You got to know the 3 plate boundaries. Those are absolutely key to knowing, understanding, this particular topic and section of the class. All right, everybody. Thanks. Be well. Have a good rest of the day or night wherever you are.